let's take a look at a couple of things here, just to prep us for this. Some of the things you recall that we went over last week. One is, if we have a circle that has two chords in it that intersect, that point of intersection has a special relationship with the two chords. The point of intersection divides those two chords into pieces that have the same product. What do I mean by that? Well, let's say that this chord here is cut into pieces that are 6 and 12. What's 6 times 12? 72. Let's say that this chord here, that this piece is 8 inches long, or 8 units long. Whatever this piece is, 8 times that has to multiply also to 72. So we're going to take the 6 times 12 and divide it by 8, and we do get 9. That piece has to be 9. 6 times 12 is 72. 8 times 9 is 72. The product of them, not the sum. The product. Notice that they don't add up to the same. 6 plus 12 is 18. 8 plus 9 is 17. They don't have to add to the same number. The two pieces have to multiply to the same number, the same product. Now, the other things that we looked at dealing with circles, pretend that's a circle. If we have a chord of a circle, and it is intersecting a radius or a diameter of that circle, if the radius intersects that chord at a right angle, in other words, if it's perpendicular, it cuts that chord in half, like that. Those two pieces are equal. On the other hand, if we have a chord and a radius, the opposite is true. If that radius cuts the chord in half, then it must intersect at a right angle. So a lot of times in math, it doesn't go both ways like that. One causes the other, but not necessarily the other way around. In this case, yes, it does go both directions. If a radius cuts a chord in half, then they're perpendicular. If a radius is perpendicular to the chord, then it cuts it in half, both ways. So up here, this is a diameter, so obviously it's also a radius, or a piece of it at least is the radius, and it's perpendicular to that chord, so it must cut that chord in half. So this here must be how much? 40 inches. And this must be how much? 40 inches. So what that means, since that's a diameter is also a chord, it just happens to be a chord that goes through the center of a circle. Since there's two chords that intersect, they must be cut into pieces that have the same product again. So we've got 40 times 40 is that piece, divided by 16, which is going to give us 100. So from here to here must be 100. Now, I didn't ask you to find that distance. What I asked you to find was the radius of the circle. Well, from what we just found, do we know the diameter? It's not 100, it's what? 116 inches. We've got the 100 from here to here plus the 16 that we already had. So then the radius is 58, half the diameter. Does that look familiar at all? No? It sometimes is tough to remember, isn't it? An application of that would be, let's say that you are machining the base of a vise or the base of some other tool. And at the bottom, I don't know where that came from, stray marks. At the bottom of the piece, instead of just a flat, hollowed channel in bottom, it's going to be an arced. Yeah. And that is a true arc of a circle. And if this is across here, oh, let's go, what? 120 millimeters. And if the height above from there up is, oh, I don't know, let's go 8 millimeters. Find the radius of the circle that would create that arc. So if you expanded this circle out, what would its radius be? So now if you try that in your notes quick, see if you can get that to work. Okay, let's see where this takes us. So, if I draw in the rest of the diameter here through the center, to find that length, I'll call it X for now. Up here, I have to split this into two pieces, which each is going to be how much? 60. So to find X, X is going to be the 60 times the 60 divided by 8. Very good. So what does that give us? 450? Is that like right? So what's that? So the diameter is 458, and the radius is 229. How many of you had 229? Do you guys all see how we got to that now?
Just one less step.
Yeah. Okay. Now, here's something kind of cool. We haven't done trig yet, but there is a way, if you know the length of a chord and the diameter of the circle. So for this one, we had a chord that was 60 millimeters and the diameter of 458 millimeters. If you know the length of a chord and the diameter, you can find this angle right here. Now I'm going to put up a strange symbol. That's the symbol theta. Looks like an O with a line through it. That's the symbol that's often used for a missing angle. Instead of using X for a missing length or whatever, they use that for a missing angle. So whenever you see that symbol, all it's doing is referring to an angle of some sort. But if you wanted to find that central angle here, all it is an inverse trig function, an inverse sine of the ratio of the length of the chord to the diameter of the circle. Yeah, yeah. And what that would give you is that would give you half that angle, so you have to double that to get the full angle. But it's just, again, we'll cover that next semester. We'll talk about that. But it is kind of interesting that length, there's a lot of information you can get from this. Just by knowing the length of that chord, you know the length of the chord, and this length here, like we found, you can find the diameter from that. Therefore, you can find the central angle. Therefore, you can find the area of the segment or the area of the sector, or all sorts of different things you can find. You guys look thrilled to know that information is coming your way at some point before the end of the year. You'll just have to wait till next semester. You have to contain yourself till then. Okay. The homework we had, page 165 in the packet. 165 through 169. Let's start out on page 165. Number 1. The diameter is 10 inches. Circumference is 31.4 inches. The area is 78.5 square inches. Number 2, the radius is 6 feet. Circumference is 37.7 feet. Area is 113.1 square feet. 3, radius is 13.13 feet. Diameter is 26.3 feet. The area is 542.9 square feet. 4, radius is 5.17 inches. Circumference is 32.52 inches. And the area is 84.13 square inches. How many of you had all the first 4 correct?
Using the pi key?
Yeah, well, I'm using 3.14 or pi. If you're off by a little bit, it's probably just round off. How many of you had all of the first 4 done? Okay. Anybody need me to slow down so you can write in the answers so you can try them all later?
What was number 3?
3 was 13.13,
Right.
26.3, 26.26, and then 542.9. 5, diameter is 8 inches. Circumference is 50.27. Yeah?
Diameter 16 inches.
Did I say 8? Yeah, diameter 16, sorry. Circumference is 50.27, so obviously I was using the pi key and not just 3.14, because it would be 50.24 if I was using 3.14. And the area is 201.06. 6, radius is 1.3 inches. Circumference 8.17 inches. Area 5.31 square inches. 7, radius is 5. Diameter is 10. Area is 78.5. 8, diameter is 12.5. Circumference is 39.3. Area is 122. And 9, radius is 4. Diameter is 8. Circumference is 25.13.
I got double that.
2.25, 4.5, 14.13.
I got
So if your area is 50.265.
I don't know how I got that.
First thing you got to do is you got to divide by pi. You divide that by pi, you're going to get almost exactly 16. Right? So you square root 16.
I don't know how I got 14.13.
I'm not sure what you did there. So that would be your radius. Because when you're dealing with area, it's radius squared. So, did you get to work out this time? Did you see what went wrong? Okay. So 4, 8, 25.13. Any questions on those first 9? Number 10 is loads of fun. Basically, all you're doing on number 10, we did a problem similar to this. You're finding the area of this washer, a ring, basically. Tell you the inside is 5 foot diameter. The outside is 7 feet of diameter. So you're going to find the area of the big circle, pi times 3.5 squared, and the area of the little circle, pi times 2.5 squared, and subtract them. Where'd the 2.5 come from? Half the 5. And the 3.5, of course, is half the 7. You should end up getting 18.85 square feet. Good. Number 11. The area of that glass is just a quarter circle. I get 201.06. Number 12. 254.5.
That's number 13.
60.
Oh, sorry. Number 12, I got 57 and 1/8. Still didn't get it? Okay, so the nearest eighth inch was the perimeter of the window in exercise 11. So you've got this window. It's 1'4" radius, so it's 16 inches, right? So you've got 16 inches and 16 inches. We need to find this quarter circumference here. So we're going to find the circumference of the whole circle, which will be pi times 32, then divide by 4. Right? That's 1/4. That'd give you this arc length out here. So that's going to be 25.12 about. Right? Plus 16 and 16 is 57.12. Now it says the nearest eighth inch. So we're going to take off the 57. And we're going to take the 0.12 and turn it into a fraction by putting it over 1. And then we're going to multiply to turn it into 8. So multiply by 8 over 8, which is going to give us 0.96 over 8. 0.96 rounds to 1/8. So 57 and 1/8 inch. 13 is 254.5. 14, 9 square feet. 15, 11 feet. 16 is 10 inches. And 17 is 8.23 square inches. 8.23. Any of those you want me to go over? I'm guessing maybe 17. Sure. So 17, you got a tapered post. 3 1/8 on the top, 4 1/2 on the bottom. What is the difference in cross-sectional area from the top to the bottom? So on top, you got a circle that's 3 1/8. So that's 3.125, which means it's going to be 1.5625 inches in radius. So the area at the top is pi times 1.5625 squared. At the bottom, then you've got 4, a little bit closer to scale. Yeah, so at the bottom, you got 4 1/2. So that's 4.5 with a radius of 2.25. So that's pi times 2.25 squared. And you should subtract those, it should be 8.23. Let's multiply that out. So pi times 1.5625 squared, 7.67, and then pi times 2.25 squared is going to be 15.90. So 8.23 exactly. Approximately, because we're using pi, so it's always approximate. Any other questions? Okay. Number 18 on page 167. 0.44 square inches. 19, 14.14 inches. 20. I'm guessing we'll have to go over 20. I get that you need a pipe that's at least 3 inches in diameter. Let's go over 20. What they're saying is you've got 2 1.5 inch pipes. And 1 2 inch pipe. All flowing into a main line. So if you're doing, this is going to be more for like a sewer plumbing or for, in the reverse of, what's that? Yeah. If you're plumbing sewer, you need to have the inflow and need to have the outflow match up. Or if you're doing a duct work for a heating system, you'd do this in reverse. You would start at each of your outlets. Well, the size of each of your outlets, and you'd take those sizes, and that's how big your main line has to be to get enough airflow to push air through each of the outlets. Yeah, there's stuff like that. So we need to know how big does this main line have to be, so that if each of these inlets were coming at full volume, there's enough volume in the main line to handle it. All we're really looking at is cross-sectional area. Now, by the word cross-sectional area, all that means is if I cut something off, if I were to cut the pipe off, I'm going to get a circle. What's the area of that circle? I cut each of these pipes off, I get a circle. Well, I've already kind of got the circle drawn at the end there where it's labeled. So we need to find the total area of these three pipes that are going in. So the first one has a diameter of 1.5, so has a radius of 0.75. So that's pi times 0.75 squared, and then it's going to be times 2 because there's 2 of them. So I get the area of those two together. Each of them is about 1.76. Together they are 3.53 square inches. So that's the two 1.5 inchers. Now the 2 incher, that's pi times, what's its radius? 1 squared. So that's going to be 3.14. So I add that up, I get 6.67 square inches. That's the total inlet area of that system. So the main pipe has to have an area of at least that much. And we're going to round to the nearest 1/4 of an inch, I believe. Yes. Round up to the next 1/4 inch, it says. So we're going to take 6.67 and we're going to work backwards from an area to a radius, which means we're going to divide by pi. Which will give us 2.123. And then we're going to square root it. So second square root, second answer. Telling my calculator to square root the previous answer. 1.46. That would be a radius. So to make it a diameter, now I did leave out the square root step in there. So you divide by pi, then I square rooted it to get the 1.46. So I've got to double that to get a diameter, which is going to be 2.92 inches. And round up to the next 1/4 inch. Well, the next 1/4 inch would be 3 full inches. Kind of an involved problem. A little bit of a long one. That'd be a good problem to put on a quiz or a test someday. Next year? Yeah, next year's group should really have that. They should really know that next year. Yeah. Number 21, I get 8.29 square feet. And 22, 34.9 inches would be the radius of that circle. That's just like the ones we did at the beginning of class today. Any questions?
Number 22.
Yep.
The packet gives the formula on page 161.
Yeah, kind of an ugly one.
That's what I'm using, and I'm getting humongous numbers.
So let me get this labeled in here. We got 36 inches and 5 inches. So the 161 the formula here. They are taking W squared plus 4H or plus 8H. That should be W squared divided by 8H. Yeah, their formula is wrong. That formula does not work.
Alrighty then.
So yeah, that won't ever work out.
So it's divided by 8.
It should be divided by 8H. So what you have here, 18 and 18. So if I'm going to label this down here as x, pretend that goes through the center. X is going to be 18 times 18 divided by 5. Well, 18 times 18 divided by 5 is 324 divided by 5, which is 16.8, right? Correct? No. 64.8. So then we add the 5 to that, gives us 69.8. Is our diameter. What's that?
Half of h, the height, so 2.5.
5? No, we got to add the full end. You're looking at the formula still. We're just going step by step off the circle concepts. We'll come back to the formula and see how the formula works in just a second. So then 69.8 divided by 2 gives us a radius 34.9. Now that formula, which I've never really cared for, is take W, which is 36, square it, divide by 8h, which is 8 times 5. That has to be in parentheses. You're going to do the 8 times 5 before you divide. And then to that, when you're all done, you're going to add 0.5 times 8. So 0.5 times 5. So 36 squared is 1,296, right? Divided by 40 is 32.4, I believe. Right? Plus 0.5 times 5 is 2.5, which is 34.9. The other, yeah, the formula to me is it's just another extra thing to memorize. Yeah, you're going to be one of those that likes to crank out formulas, huh? That's fine. The book gives formulas too. That's what almost every book does, is gives formulas, so you'll be fine. I don't like have to memorize more things than I have to, so I see the basic concepts and I figure it out as I go rather than memorize formulas.
Do you know of any place where you can get all the formulas?
Not really, no. What I always recommend is just, take like the back cover of your notebook or the last page of your notebook or something, just start making your own list and write them down. Because a lot of times they make more sense to you anyways if you write them down and label them yourself as to what everything means, so it's in your own words.
Then you need a math file.
Well, that's what
Figure out how to use it.
in your average Microsoft Word, there's a symbol, insert symbol and insert equation function that has all those math things in it. In Word, yep. Here in Word, if I were to go to insert, then over here you got symbol. Equation won't work right now because I'm in compatibility mode. But symbols, you got all your math symbols there. If I wasn't in compatibility mode, you could do, here, I'll just bring up a new one for this. So, insert equation. I can put in all my different fraction types, square roots, integrals, which you guys won't get into, that's calculus. Different things, all my math symbols here, multiply, equals, divide, all that stuff is in there. Like for your errors, plus or minus.
How do you type in multiple levels?
Multiple levels? Like, what do you mean? Like
Like a fraction?
Like, well, not just a fraction, but a formula over divided by something or divided by another formula.
so you click in the fraction here. Then you type whatever you need on top. The only tricky part is if you're going to put in squared, like x squared, you got to put x. You got to click on the thing first, then type in the x squared. Like that.
Graphing function equation.
I've never seen that word.
Yeah.
That's under what?
That's under insert, and then over on the right side. You click on insert, then it's over here. You got symbol, which is all the different mathematical symbols. There's actually a whole list you can pull up. You can get You can see the scroll bar. You can scroll up and down. There's a couple thousand of them there you can pick from.
That web names?
What's that?
That web names?
Some of those are in there, yeah.
They're fun.
Yep. Okay. So number 23, 12 foot 6 and 13 sixteenths, or 150.8 inches. And number 24, 27.08 inches. How are we feeling? Wonderful? We should probably have a quiz. Did you just ask me for a quiz? Really?
No. You've been drinking this long, you did?
Okay. Well, Dustin's life is not in jeopardy. Let's get on with things. No, Dustin's smart because he knows that I don't want him to get hurt in the hallway. So now I can't give you a quiz.
Exactly.
Or you're going to blame it on him. See? He is a smart move.
See, he's taking the class before he knows it. Give him the quiz.
I took it with, I think I've taken this class before or something like that with,
What program are you in?
architectural design.
You took tech math, which probably would have covered this class. Yeah, you probably had Linda. That would have probably covered this class if you'd asked for it to transfer.
I got A in it.
Yeah, that probably would have covered it. So,
You're tired, so you didn't take it.
we're going to look at octagons. This is a shape that comes up enough in machining if you have octagonal stock. Also comes up in construction quite a bit. Basically, anytime you take a square and you clip the corners to relieve the corners, you're going to end up with some form of an octagon. What we're going to look at today, of course, are what we call regular octagons. Regular just means all the sides are the same length and all the angles, all the interior angles are the same. So kind of like I attempted to draw here. There are some features of the octagon that we are going to use. Capital S is going to be the length of a side. Capital D is something we call a diagonal. It goes from corner to opposite corner, that length. And then F is what we call the flat dimension. It goes from side to side at a right angle like that. So you can see that D is always going to be slightly larger than F. D is significant to us because if we're trying to create an octagonal piece from a piece of round stock, D would be the diameter of the smallest round stock that we could clip to make that octagonal piece. If we're going the other way, if we had a piece of octagonal stock and we wanted to make it round, F would be the maximum diameter of round stock that we could get, or round piece that we could get by machining down, by turning down that piece of octagonal stock. Make sense? Now, I'll admit the octagons are a little bit more useful in construction than they are machining, but it's still worth seeing this. So let's say I want to find the area of this octagon. If I am using D, the diagonal, the area of that octagon is 0.7071 times D squared. So if I have a round piece that has a diameter of 1.75 inches, and I'm going to clip that down to make it an octagon, the most efficient octagon I can get, the largest octagon I can get out of that round piece, what's the area of that going to be after I clip it down? to make it round or make it octagon? Well, D would be the diagonal, corner to corner. So that's going to be 0.7071 times 1.75 squared. What'd you get?
2.165.
Perfect. 2.165 inches squared. Or we could also, looking for the area, if we wanted to use the flat, 8.8284 times the flat dimension squared. So if I have a piece of octagon stock, or of octagon material, and I put a caliper on it, or a micrometer or whatever, and I measure this dimension across there, and it comes out to be 28.5 millimeters. And I want the cross-sectional area. That cross-sectional area is going to be 0.8284 times 28.5 squared. $672.868 millimeters squared. Or, let's say I knew the length of the side. The area, if I know the length of the side, is 4.8275 times the length of the side squared. I use this formula a lot because I do construction. And I specialize in decks and gazebos and stuff like that. Most of your gazebos are octagons. So I'll have somebody that'll come to me and say, hey, I want a gazebo, and I want the side of the gazebo to be 6 feet. So I need to figure out my square footage, and I bid it off of a square footage. So that square footage is going to be 4.8275 times 6 squared. Which is 173.79 square feet. Now, another application of these formulas is this. Let's say, I'm going to go with a construction example again, just because, well, I can.
This is only for a regular.
Only for a regular octagon, yes. It must be regular.
Have you ever seen the irregular?
Yeah. I mean, you take a square and you clip the corners off. Often it's irregular. You have 4 sides that are one dimension and 4 sides that are a different dimension. You take a square and you're just going to clip the corners off to relieve them. Often what you clip off isn't a full, full side. It's just a little clip to relieve it. And it's an octagon, but not a regular octagon. That's the most common type of irregular octagon you're going to see, is where you have 4 sides that are one length, and then the other 4 sides that are somewhat short, slightly shorter length. That one's a little tougher. We'll go through that one when we do trig next spring.
Kind of like the top of a nut or bolt.
Bolt head should be perfect octagon. It's supposed to be. No, it is. You're right. It's a hexagon. Yeah.
I thought we relieved just the.
Yeah, because it's a 12-point socket or 6-point socket. So yeah, it's a perfect hexagon for a bolt. So anyway, let's say that I have someone that comes to me and they want a gazebo built. And they want it to have 8-foot sides on it. I want to know, when I go to frame this, I'm going to put joists across here. And then I'm going to frame out. I want to know if I can use standard lumber for joists, or if I'm going to have to splice or get LVLs, or what I'm going to have to do. So I want to find out what that length is across here. In other words, I want to find out what dimension. Not the D, I want to find out F, the flat. D would be corner to corner, right? So I'm going to find the area of this first, the 4.8275 times 8 squared. 308.96, you got it. That's square feet. Now I'm going to work backwards. The area from the flats is 0.8284 times the flat squared. That's got to equal that. So I'm going to work backwards, which means I'm going to divide that by the 0.8284. Which is going to give me 372.96. And then I'm going to square root that. So second square root, second answer, 19.31. So that's telling me there's 19.31 feet across the flats. So I could buy 20-foot lumber for joists if I wanted to. Don't really think I would want to. 20-foot lumber, green-treated lumber is extremely heavy. Considering 20-foot, you'd have to have at least 2x10, probably 2x12, depending on your substructure. Anyway, enough of that. Oh yeah. In your packet, on page 170, you have 1 through 5 there dealing with octagons. That should be the last page of your current packet.